Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of magnetic fields. So in this revision session we're going to look at how to answer examination questions for A-Level AQA Physics Paper 2, in particular magnetic fields. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions on magnetic fields, assess our understanding on A-Level Physics for magnetic fields, understand what topics we need to improve upon for A-Level Physics and in particular magnetic fields, and then see what we can then develop from this. So how should we prepare for this revision session? Well, when you're completing this work in your revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand section. In this section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising your A-Level Physics examinations? So firstly, learn the key facts. Use the revision guide, the class workbooks, the student prep notes and the textbook to learn the key ideas of the course, and you may wish to make mind maps or to write out the notes yourself. Secondly, retrieve your key understanding by using Caboodle, using Seneca, using student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Okay, and then third, practice examination questions. So use exam prep books, use homework books, use supervised study books and additional workbooks to answer examination questions, then mark your own work. Now you may wish to download your own exam past papers to do this. So the three steps of learn the key facts, then testing yourself, and then practicing exam style questions are how you should be revising for your A-Level Physics exam. Now what questions will you have in this revision session? Well, you'll have three types of questions. Firstly, you'll have general check questions, which are basic questions designed to probe your understanding of key concepts of the topic. You can then have checkpoint questions, which are the more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. Then finally, we'll have assessment point questions, which are past paper examination questions, which will mimic the type of questions found in public examinations. So let's now have a look at some questions for magnetic fields. So the first question says, explain why a current carrying wire experiences a force when placed close to a magnet. Then a current carrying conductor in a uniform field is shown. Use Fleming's left-hand rule to determine the direction of the force experienced by the conductor in each example. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's the idea that the current carrying wire itself produces a magnetic field because it is moving, or it has charged particles moving in the same direction. Therefore, this magnetic field of the current carrying wire interacts with the magnetic field of the magnet and produces a force on the wire and on the magnet. Now you've got to use your left-hand rule with your thumb showing the direction of the motion or the direction of the force. The first finger showing the direction of the magnetic field from north to south, and the second finger showing the direction of the current as shown on the diagrams. So you orientate your finger in the first one and it goes into the board or into the screen. The second one, your thumb will be pointed upwards, the force is upwards, and then finally the force will be downwards because that's the direction your thumb will be pointing in. So in the next question, it shows three examples of current carrying conductors in magnetic fields. For each example, whether there will be a magnetic force on the conductor, and if there is a force, in which direction will it act in. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, there is no force. Why is that? Well, it's because the magnetic field and the current are parallel to each other, and when that's the case, no force is exerted on the current carrying wire. Now, in the second one, because the current is perpendicular, there will be a force, and therefore you can use your Fleming's left-hand rule to work it out, and the force is into the plane of the paper, or into the screen, or into the board. And then the last one, once again, you work it through, and the force is acting downwards on the page. The next question says, calculate the force per centimetre length on a straight wire placed perpendicular to a magnetic field of flux density 120 milliteslas carrying a current of 5 amps. Then a current carrying wire is placed perpendicularly to a uniform magnetic field and it experiences a force of 5 millinewtons. Determine the force on the wire when separately the current on the wire is quadrupled, the magnetic field density is doubled, and then the length of the wire in the field is reduced to 30% of its original length. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, we're using our equation F equals BIL, but because we're working out the force per centimetre, we've then got to set that length L to be a centimetre, which is 0.01 metres. So you pop in all the values, milliteslas turns into teslas, 10 to the by times 10 to the minus 3, so you work it out to be 6.0 times 10 to the minus 3 newtons. In this next one, we know F equals BIL, so if I is quadrupled, F will be quadrupled, so it goes from 5 millinewtons to 20 millinewtons. Again, in this next one, F equals BIL, B is doubled, so F will double, so therefore it equals 10 millinewtons, and again, L is proportional to F, so therefore F decreases by a factor by 30% of its initial value, so therefore it's 1.5 millinewtons. The next question says, a conductor of length 0.20 meters lies at an angle of 25 degrees to a magnetic field of flux density 0.050 teslas. Calculate the force on the conductor when it carries a current of 400 milliamps. Then secondly, underneath you'll see a picture. What force will be exerted on each of the currents shown below, and in what direction will each of the forces act in? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've now got to include the angle in our F equals BIL equation. So F equals BIL sine theta, pop in all the values, milliamps turns into amps by times 10 to the minus 3, so it's 1.7 times 10 to the minus 3 newtons. And then we know for the first one that F equals BIL sine theta, so therefore we can work it through, pop in all the values, we know it's going to be equal to 0.38 newtons. Okay, in the second one, we know F equals BIL sine theta, again sine 45 from looking at the particular values, so it's 0.27 newtons. But C, because the current is parallel to the magnetic field, sine 0 equals 0, so therefore F equals 0, so there's your answer. Now for A and B, because they've both got a force, we can work out the direction, use the left hand rule to work it through. They're both in the direction of the plane of the screen, so they're going inwards. The next question says, find the force acting on each of these particular particles. A helium nucleus travelling at 15,000 kilometers per second when the field strength is 2.2 milliteslas. An electron in a magnetic field strength 1.3 teslas travels at 320,000 meters per second. Then a sulfate ion SO2- travels at 75 meters per second in a field strength of 0.14 teslas. So pause the video now, then unpause the video when you want to go through your answers. Right, for this one, what's the force on a charged particle? F equals BQV. Popping all the values working through, helium nucleus has a charge of 2 plus because it's 2 protons in there, so you can work it through to be 2 times 1.6 times 10 to the minus 19 for its charge. Popping all the other values, kilometers per second turn into meters per second by times of 10 to the 3, milliteslas turn into teslas by times by 10 to the minus 3, so we get 1.056 times 10 to the minus 14 newtons. Same equation next time, bit easier in terms of the charge, it's just 1.6 times 10 to the minus 19, popping all the values through, 6.56 times 10 to the minus 14 newtons. This one, remember the charge is 2 minus, so it's 2 times by 1.6 times 10 to the minus 19, popping all the values, 3.36 times 10 to the minus 18 newtons. The next one says, each of these cases describes circular motion due to the effect of a magnetic field on a moving charged particle. The track of an electron has a radius of 2.5 micrometers in a field of 3.3 teslas. How fast is it moving? Then a particle is moving at 1.57 times 10 to the 6 meters per second in a magnetic field of 0.39 teslas. The radius of motion is 42 millimeters. Find the charge to mass ratio. Then an electron is traveling at 0.1 C in an experimental solenoid with a magnetic flux of density of 24 teslas. What will the radius of rotation be? So pause the video now, then unpause the video when you want to go through your answers. Right, in terms of a moving charged particle, you've got to remember that for a moving charged particle, R is equal to mv over bq. That equation is not given to you in your exam. It's the idea that the centripetal force, mv squared over R, is equal to the magnetic force, bqv, so you can work it through to work out R. So you can pop in all the values, rearrange, make V the subject, micro turns into just meters by times and 10 to the minus 6, pop in all the values. You know the charge of an electron, 1.6 times 10 to the minus 19. You know the mass of an electron given to you on the equation sheet, 9.11 times 10 to the minus 31 kilograms. So you get out 1.54 times 10 to the 6 meters per second. Once again, here you need to find the charge to mass ratio. So when you have R equals mv over bq, you want q over m, that's charge to mass. So you can work it all through, and we get 9.58 times 10 to the 7 coulombs per kilogram. Now this next one, again working out R, so R equals mv over bq. We know the mass of an electron, like we said before. Remember it's at 0.1 c, so that's 0.1 times by 3 times 10 to the 8. We know the charge of an electron, 1.6 times 10 to the minus 19, so it's 7.12 times 10 to the minus 6 meters. The next question says, if a bar magnet causes a magnetic field with a flux density of 20 milliteslas perpendicular to the plane of area A, how much flux will be contained by this area if it's 10 centimeters squared? Then a uniform magnetic field has a flux density of 5 times 10 to the minus 5 teslas and is at an angle of 75 degrees to the region of area A. How much flux will be contained by this area if it is 1 centimeter squared? Then Zora takes a wire and winds it into a coil of 10 circular turns with a radius of 5 centimeters and then holds this in a magnetic field with a strength of 20 milliteslas. What is its flux linkage? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's our equation for flux? Flux is equal to BA. It's the magnetic flux density times by the area. So it's 20 milliteslas into teslas times 10 to the minus 3. Work out your area now. Centimeters squared into meters squared is times 10 to the minus 4, because there's 2 times 10 to the minus 2 because it's centimeters squared. So we get 2.0 times 10 to the minus 5 Webers. This next one now, because we've got an angle, it's actually flux is equal to BA cos theta. Pop in all the values, convert centimeters squared into meters squared again, and we get 1.29 times 10 to the minus 9 Webers. And then this last one, now we've got to consider what the flux linkage is. So flux linkage is going to be equal to n phi or n flux, so therefore it's n BA cos theta. So you pop in all the values. Now remember, area in this instance is going to be pi r squared, so it's going to be 5 times 10 to the minus 2 because you go from centimeters into meters. So you can pi times by 5 times 10 to the minus 2 squared. We know in this instance cos theta equals 0, so it's going to equal 1. Pop in all the values and we get 1.6 times 10 to the minus 3 Weber turns. The next question says, in Britain the magnetic flux density is 50,000 nanoteslas with the field approximately at the horizontal. Firstly, estimate the flux passing through your body if you are standing vertically and facing north. Then a typical smartphone compass uses a small magnetometer chip to determine which way the phone is facing. Such chips are typically 2 mm by 2 mm squares. If you held a smartphone so that the magnetometer chip was at an angle of 20 degrees to the horizontal, what would the flux passing through the chip in the phone be? Then in an electrical motor, a permanent magnet of flux density 18.4 milliteslas has its field placed perpendicular to a coil of 250 turns of copper wire. The diameter of the coil is 8.50 centimeters. What is the flux linkage between the field and the coil? So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So the first one, you're going to have to estimate the area of a human's body. So if let's say roughly that a human is 2 meters tall and 0.5 meters wide, so roughly we're looking at 1 meter squared. So therefore we say theta equals BA, pop in all the values, nano turns it into teslas by times and 10 to the minus 9, so it's 5 times 10 to the minus 5 times 10 to the minus 5 Webers. Now in this next one, we know that the flux is equal to BA cos theta. We pop in all the values. Now again, remember it is a square, but it's in millimeters, so it's 2 times 10 to the minus 3 times by 2 times 10 to the minus 3. Pop in our angle there 20 degrees, so we get 6.8 times 10 to the minus 11 Webers. Again, same equation now for flux linkage, except it's n phi, so therefore it's n BA cos theta. So we pop in now 250 turns. We work out area because it's pi r squared. So you give the diameter, half it get the radius, turn that into meters, then you work it through, so we get 0.0261 Weber turns. The next question says, a straight wire of length 0.20 meters moves at a steady speed of 3.0 meters per second at right angles to a magnetic field of flux density 0.10 teslas. Use Faraday's law to determine the EMF induced across the ends of a wire. Then a search coil of wire having 2,500 turns and an area of 1.2 centimeters squared is placed between the poles of a magnet so that the magnetic flux passes perpendicularly through the coil. The flux density of the field is 0.50 teslas. The coil is pulled rapidly out of the field in a time of 0.10 seconds. What is the average EMF is induced across the ends of the coil? So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work it through? So Faraday's law states that the EMF induced is equal to the rate of change of flux linkage. So the first thing to do is work out the change in flux. So what you can say is B times by the change in area. So you work that through, so you get it to be 6 times 10 to the minus 2 Webers. So therefore EMF is going to be the change in flux linkage. So that's going to be 6 times 10 to the minus 2 divided by the time, which in this instant, if you're working at 3 meters per second, and you've worked out that the area is 3 meters times by 0.2 meters, therefore we can say the time is 1 second. So you pop that through to be 0.06 volts. Now this next one again, flux linkage is equal to nth I, so it's BAN. So you work out the magnetic flux linkage by doing 0.5 times by 1.2 times 10 to the minus 4 centimeters squared into meters squared times by 2,500. That gets you 0.15 Webers. Now you'll notice when you're out the field, the flux linkage will be 0 Webers. So therefore the change in flux linkage will be 0.15 Weber turns, because it's 0.15 minus 0. You then divide it by the time, 0.10, so it's 1.5 volts. The next question says, determine the peak voltage if the RMS voltage is 10 volts, 40 millivolts, 25 microvolts. Then determine the RMS voltage if the peak voltage is 45 volts, 7 millivolts, and 100 microvolts. So pause the video now, then unpause the video when you want to go through your answer. Right, this is just using our equation that the peak voltage is equal to the root mean square voltage times by square root 2. That's an equation given to you on your exam. So it's 10 times by square root 2, 14.1 volts. Next one, it's going to be 56.6 times 10 to the minus 3 volts. And then finally, it's going to be equal to 35.4 times 10 to the minus 6 volts. We rearrange it for the RMS voltage. So VRMS equals V0, the peak voltage, over square root 2. So it's 45 over square root 2, 31.8 volts. This next one, millivolts turns into volts by times 10 to the minus 3. So it's 4.9 times 10 to the minus 3 volts. Then here, it's going to be 70.7 times 10 to the minus 6 volts. This next question says, for each of the images determine the peak voltage, the RMS voltage, and the frequency of the signal. So pause the video now, then unpause the video when you want to look through your answers. Right, so in this question, how do you work it through? So in the first one, how can you work out what the peak voltage is? Well, you look on the screen, you see that you're given the Y gain and it's set to be 5 volts. So therefore there's three squares between the equilibrium and the peak. So therefore 3 squares, each of 5 volts, it's 15 volts. Now in terms of the RMS, we know that VRMS is that V0, the peak voltage, over square root 2, so it's 10.6 volts. And therefore in this next one, we know that frequency is 1 over time period. Now you'll see that the time base is equal to 2 milliseconds for each square. Now you'll see that one entire wave is equal to 4 squares, each of 2 milliseconds. So the entire period of the wave is 8 milliseconds. So the frequency is 1 over 8 milliseconds. It's 125 hertz. So we do these next 3 examples are all the same principle. 4.5 squares, okay, each of 0.5 volts. So the peak is 2.25 volts. VRMS is going to be 1.59 volts. So therefore the time period is 8 squares, each of 1 milliseconds. The time period is 8 milliseconds. Frequency is 1 over 8 times 10 to the minus 3, 125 hertz. C is going to be equal to a peak of 0.5 volts, a VRMS of 0.32 volts, and then a time period of 25 hertz. And then this last one, they're 4 squares, each of 0.2 volts, so the peak is 0.80 volts. The VRMS is 0.57 volts. And then finally, you can work out that the time period in total is 200 milliseconds. So therefore, the frequency is 1 over 200 times 10 to the minus 3. It's 10 hertz. The next question says, a step-down transformer changes 230 volts mains voltage to 5 volts. The transformer has 920 turns on its primary coil. Calculate the number of turns on its secondary coil. Then an old mobile phone charger has an inbuilt transformer that produces an output voltage of 5.2 volts. The input voltage is 230 volts and the primary coil has 500 turns. Calculate the number of turns on the secondary coil. Then an electronic device uses a transformer with a turns ratio of 20:1 to step down the mains voltage from 230 volts. Calculate the output voltage from the transformer. Then a transformer is used to step down a 230 volts mains voltage to 12 volts. A 60-watt lamp connected to a secondary coil is lit normally. The primary coil has 1000 turns. Calculate firstly the number of turns on the secondary coil, and then secondly the number of the current in the primary coil. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using our transformer equation, which is Ns over Mp equals Vs over Vp. N is directly proportional to V in a transformer. Pop in all the values so you get out 20 turns. This next one again, we're using Ns equals Mp times by Vs over Vp. Again, the transformer equation, the equation given to you in your exam, we get 11 turns. That feels right because the secondary voltage is lower, so therefore the number of turns should be lower as well. This next one, again, we can see that it's a ratio there of 20:1, so therefore you can work it all through and you get your value out to be 12 volts. This next one again, we are working it through again and we pop in all the values, work it through, and we get 52 turns. Again, that feels right because the number of turns on the secondary is much lower, than the primary, but also the voltage is much lower. It's gone from 230 to 12, so therefore the number of turns will also decrease by a great amount as well. And then finally, what's the current going to be? Well, it's going to be current is equal to power over potential difference. It still works because it is the same. It's the same principles of electricity. So you get out 0.26 amps. The next question says, an iron core has a square cross section with each side being 4 centimeters. The primary produces a magnetic field with a strength of 0.5 teslas. This takes 60 milliseconds to generate and die away when the primary circuit is switched on or off. The secondary coil has 120 turns when the EMF will be induced in the secondary at the moment of switch on or switch off of the primary circuit. So there should be what EMF should be induced. Then secondly, a local substation of the national grid changes the voltage down from 11 kilovolts to 415 volts. If the primary coil in this transformer has 8000 turns, how many will be needed on the secondary coil to give the correct output voltage? So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how to work out EMF? EMF is the change in flux linkage divided by the change in time. Flux linkage is going to be BAN, so we can work out what A is going to be because it's a coil, so therefore, it's a square cross section, my apologies, so it's 4 centimeters, which is 0.04 meters, times by itself, so it's 0.04 squared. Okay, we know the number of turns, 120, we know what B is, it's going to be 0.5, we then divide it by the time, which is 60 milliseconds, so it's 60 times 10 to the minus 3, so therefore it's equal to 1.6 volts. This next question here, we say Ns equals Mp times by Vs over Vp. It's that transformer equation again. We work it through. Remember, kilovolts turns into volts by doing times by 1000 or 10 to the 3. So we get our 302 turns. That feels right because we've gone down by volts a lot, so we're going to go down by turns a lot as well. The next question says, explain why a stationary charged particle in a magnetic field does not experience a force. Then calculate the maximum magnetic force experienced by an electron travelling at a speed of 6 times 10 to the 5 meters per second in a uniform field of flux density 0.20 teslas. Then a particle of charge plus 2e describes a circle of radius 2.5 centimeters in a uniform magnetic field of flux density 300 milliteslas. Calculate its momentum. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to have the understanding that the force given on a moving charged particle is F equals BQV. So V is 0, F is 0. Again, we're using F equals BQV, pop in all the values, work it through, we get 1.92 times 10 to the minus 14 newtons. Look at the equation sheet for that equation. Now, because it's going in circular motion, we can say, remember, R equals mv over bq, because the centripetal force is the magnetic force. Pop it out. Now we know mv is momentum, because momentum equals mass times velocity, so therefore it equals BQR. Pop in all the values. Remember, centimeters turn into meters, milliteslas turn into teslas by times 10 to the minus 3, and remember it's a charge of 2e, so it's 2 times 1.6 times 10 to the minus 19. So we get 1.04 times 10 to the minus 21 kilogram meters per second. The next question says, electrons ejected from an electron gun at a speed of 1.4 times 10 to the 7 meters per second enter a magnetic field of flux density 2.4 milliteslas acting 90 degrees to the beam. Determine the radius of curvature of the path followed by the electron beam, given that the specific charge of an electron is 1.76 times 10 to the 11 coulombs per kilogram. Then calculate the speed of an antiproton created in a high energy collision if the radius of the curvature of the track is 0.11 meters and the detector's magnetic field strength is 3.0 teslas. Then a charged particle moving at right angles to a constant magnetic field follows a circular path, so that the radius of curvature of the particle's path is directly proportional to its momentum, and then particles of mass m and charge q travel in a circular path of radius r and speed v in a magnetic flux density b. How many of these quantities m, q, v, r and b, if increased one at a time, would increase the radius of the path? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, remember, circular path, R equals mv over bq, so therefore we can work out what these values are going to be. Now remember, specific charge, specific means per mass, per kilogram. So specific charge is charge per mass, so we can rewrite it out as is R equals v over b times by q over m, or the specific charge. Pop in all the numbers, work it through. Remember, milliteslas turn into teslas, so you get 0.033 meters. This next one again, you go V equals BQR over M. Now remember, the magnitude of an antiproton's charge is the same as a proton, so it's 1.6 times 10 to the minus 19. We work it through and it's 3.2 times 10 to the 7 meters per second. How do we show it's directly proportional? Like we said, we say that the centripetal force is equal to mv squared over r, but the centripetal force in this context is the magnetic force, which is equal to bqv. So therefore, mv squared over r equals bqv. Rearrange that to be r equals mv over bq. For a particle that's moving, q and b are going to be constants, so therefore r is directly proportional to mv, the momentum. Now, like we said, R equals mv over bq, so if you increase m or you increase v, you would increase r, but increasing b or increasing q would decrease r because of where it is on the equation. The next question says, calculate the magnetic flux passing through a small circular coil of diameter 1.5 centimeters positioned between the poles of two slab magnets, given that the magnetic flux density between the magnetic poles is 300 milliteslas. Then calculate the magnetic flux passing through a circular coil of diameter 2.0 centimeters if the magnetic flux density is 150 milliteslas and the angle between the normal to the plane of the coil and the direction of the magnetic field is 40 degrees. Then calculate the magnetic flux linkage through a 20-turn circular coil, given that the magnetic flux density is 150 milliteslas, the angle between the normal to the plane of the coil and the direction of the magnetic field is 16 degrees, and the radius of the coil is 5.0 millimeters. Then determine the magnetic flux and the magnetic flux linkage through a rectangular coil of dimensions 5.0 centimeters times by 3.0 centimeters, given that the coil has 100 turns, the magnetic flux density is 120 milliteslas, and the angle between the coil and the magnetic field direction is 30 degrees. So pause the video now, then unpause the video when you want to go through your answers. Right, in this one, remember how to work out magnetic flux. Flux is equal to B times by A. So you work out your area, you convert your 1.5 centimeters into meters by times 10 to the minus 2, and you half it because you want the radius. So you do B, so milliteslas into teslas, times by your pi r squared to work out your area. You get 5.3 times 10 to the minus 5 Webers. Now again, we've got an angle, so it's BA cos theta now. So therefore it's 150 times by 10 to the minus 3 times by cos 40 times by pi r squared. Remember, we'll give the diameter, turn it into meters, half it, so you can work it through to be 3.6 times 10 to the minus 5 Webers. This next one again, we're now working out the magnetic flux linkage, so therefore it's n phi or BAN cos theta. So we're now going to times it by the number of turns that we've got. So we do 20 times by 150 times 10 to the minus 3, because it's milliteslas into teslas, times by cos 16 times by pi r squared again, so millimeters into meters, so it's 5 times 10 to the minus 3, so it's 2.3 times 10 to the minus 4 vapor turns. And here again, flux is equal to BA cos theta, work it all through, and you get 1.6 times 10 to the minus 4 vapors. Flux linkage is n times that value, so you times that then by 100, so it's 1.6 times 10 to the minus 2 vapor turns. Remember, the difference in use between flux and flux linkage is vapors and then vapor turns. So even though the SI unit of both of them is the same, we use the differential there to differentiate between the two values. The next question says, a rectangular coil rotates at a constant angular velocity within a uniform magnetic field of 0.121 teslas. The coil has 70 turns and a cross-sectional area of 49 centimeters squared. The diagram below shows the coil look along the axis of rotation. Calculate the flux linkage of the coil when the angle is 23 degrees. Then as the coil rotates, explain what values of theta provide the maximum and minimum values of induced EMF. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's flux linkage? BAN cos theta. Popping all the values through. Now remember, you got 70 turns, so that's going to help you with that one. Okay, now that's going to help you when you work it through. Now remember, cross-sectional area, we go in centimeters squared to meters squared, so it's times 10 to the minus 4. You work that all through, and we get 0.046 vapor turns. Now you're going to get a maximum induced EMF at theta equals 90 degrees when you work it through, because even though the flux linkage is the lowest value, the rate of change of the flux linkage, which is what causes induced EMF, is at its largest. And when theta equals 0, there'll be no EMF, because even though the flux value is a maximum, the rate of change in flux is actually at a 0 value. So therefore, because it's instantaneously stopped at that point, if you think about it. Okay, so therefore you're going to get no EMF. The next question says, a student thinks that electrical current passes through the core in a transformer to the secondary coil. Describe how you might demonstrate that this is not true and explain how electrical current is actually induced in the secondary coil. Use Faraday's law in your explanation. Then a square coil of 100 turns of wire has sides of length 5.0 centimeters. It is placed in a magnetic field of flux density 20 milliteslas so that the flux is perpendicular to the plane of the coil. Calculate the magnetic flux through the coil, and the coil is now pulled from the magnetic field in a time of 0.10 seconds. Calculate the average EMF induced in it. Then an aircraft of wingspan 40 meters flies horizontally at a speed of 300 meters per second in an area where the vertical component of the Earth's magnetic field is 5.0 times 10 to the minus 5 teslas. Calculate the EMF generated between the aircraft's wings tips. So pause the video now, then unpause the video when you want to go through your answer. Now, the most obvious demonstration is to show that the secondary coil is made from insulated wire, so is the primary coil, so therefore no current can flow from the core to the secondary coil from the primary coil because it can't flow through an insulator. Now, an electrical current is induced in the secondary coil of a transformer because there's a change in magnetic flux linkage in that secondary coil, and when you've got a change in magnetic flux linkage, that will induce an EMF. When that's part of a complete circuit, that will produce a current. Now this next question, flux is going to equal BA. Pop in your values. Remember, we turn centimeters into meters. We go milliteslas into teslas. So we get 5.0 times 10 to the minus 5 vapors. EMF is equal to the change in flux linkage divided by the time. Now again, when it's out the field, the flux linkage is 0, so it's 5 times 10 to the minus 5 minus 0 when it works through. 100 because you're converting the flux into flux linkage, so you multiply that by the number of turns, but then it's minus and 0, so therefore it's going to be equal to the value. Then you divide it by 0.1. It's 5.0 times 10 to the minus 2 volts. Now this last one, another trick you can use, because another equation which isn't given on your exam sheet, but you can learn it to work out your average induced EMF, is BLV, where V is the velocity. So you can pop in all the values, work it through, and you get 0.60 volts. The next question says, a single phase AC power supply has an RMS voltage of 230 volts. Calculate the peak value of the power supply, and then calculate the average value for the power supply. So pause the video now, and then unpause the video when you want to go through your answer. So, how to answer this particular question? Well, remember the equation is that Vp is equal to Vrms times by square root 2. So if you work that through, you can see that values out to be 325.27 volts. Now the average value is therefore going to be V average is going to be 2 times by V peak over pi, working through, thinking about it as if it was a complete circle, working it through, so you get 207.1 volts. Okay, now this next question says a conductor with a length of 250 millimeters is moving at a right angle through a magnetic field of flux 2.2 teslas. The conductor is moving at a velocity of 8 meters per second. Calculate the induced EMF. So pause the video now, then unpause the video when you want to go through your answer. Right, like we said before, there's a bit of a shortcut equation when you're given the velocity and you want to work out the average induced EMF. So EMF is equal to BLV. Now we know L is given in millimeters, so it needs to be into meters, so it's 0.25 meters. Pop in all the values and you get 4.4 volts. The next question says, what is the value of current I when time equals 5 milliseconds and in which direction is it flowing? Then at what time does the current next have a value but negative? What is the time for one complete circuit? And then what is the frequency of the alternating current given the information below? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, for alternating current, we know that at 5 milliseconds you look on the graph and the value is going to be equal to 2 amps and it's a positive value, so it's moving in a positive direction. At what time will have the next value but negative, so look for -2 on the graph, so therefore it'll be at 15 milliseconds, so I'm looking at this information. Now if you look on here, the time for one complete cycle is one whole wave, so therefore you're going to be equal to 20 milliseconds is the information given on the graph. So the frequency is going to be, frequency is 1 over time period, so it's 1 over 20 milliseconds, which is 20 times 10 to the minus 3, so it equals 50 hertz. The next question says, what is the average power dissipated when a sinusoidal alternating current with a peak value of 3 amps flows through a 100 ohm resistor? Then a sinusoidal voltage of peak value of 325 volts is connected across a 1 kilo ohm resistor. What is the RMS value of this voltage? Use V equals IR to calculate the RMS current which flows through the resistor. Then what is the average power dissipated in the resistor? And then what is the peak power dissipated in the resistor? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we can use our equation that P equals I squared R, but because we're using alternating current, we need to use RMS values, average values, okay, which is RMS values. So therefore we say P IRMS squared times by R. We can work out what the RMS value is by doing the peak divided by square root 2. So therefore you would do 3 divided by square root 2. You would then square it to then get your value. You then multiply that by the resistance, which is 100 ohms, to get 450 watts. Here we know Vrms is the peak voltage over square root 2, so it's 230 volts. We can then work out IRMS because we can say, well, if V equals IR, I equals V over R, but again remember resistance is a scalar, so it doesn't need to be considered with an RMS, but V has to be because it will need an RMS consideration, so therefore use VRMS, not V peak, so it's 230 over 1000 is 0.23 amps. Then the average power dissipated, well, you'll do P equals I squared R, but the average when you've got an alternating supply is RMS, so it's IRMS you're going to be using, so you get it through to be 53 watts. When you want to work out the peak dissipation, you'll use the peak current, the peak potential difference I should say, or the peak voltage, so therefore it's going to be equal to 325 squared over R over 1000, which is 110 watts. The next question says, figure 4 shows the trace of an oscilloscope connected across a 20 ohm resistor. The oscilloscope grid is marked in centimeters and the time base is set to 0.2 milliseconds per centimeter. The Y amplifier sensitivity is set to 0.5 volts per centimeter. When the oscilloscope was first connected, the whole wave could not be seen on the screen. Describe how you'd adjust an oscilloscope to achieve a screen that's easy to take readings from. Then determine the frequency in hertz of the signal. Then determine the RMS voltage in V, and then calculate the mean power in watts transferred into the 20 ohm resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how would you get easy readings from it? Well, the first thing is adjust the time base, so you got a complete wave seen on the screen. You then move the wave either left or right, so then you can have the start of the cycle on a grid line, because it's very important. You always have key marking points on key graduations or key lines on your screen. You then adjust the Y amplification, so you've got the peak to peak as at a maximum, and then move the wave up and down, so once again the peak is on the line, so then it's easy to read. Now the frequency is 1 over the time period. You'll see the time period on the screen was equal to 6 centimeters, which was 0.2 times 10, times each one by 0.2 times 10 to the minus 3, because that was the scalar factor. So that therefore is equal to 1.2 times 10 to the minus 3 seconds. So therefore f is 1 over that value, so it's 830 hertz. Again, you can work out the peak to peak. So the peak to peak is 6 squares, so therefore the peak voltage is 3 squares. It's better to do the peak to peak because you'll have a low percentage uncertainty, then half it. Therefore you work out the voltage is 1.5 volts, but using your scaling factor, Vrms is V0 over square root 2, so therefore it's 1.1 volts. Then the mean power transferred, well, P equals V squared over R. Now it's Vrms because we want an average value, or mean value, so therefore Vrms is 1.1 volts, so you work it through to be 0.056 watts. The next question says, consider the following jumping ring experiment. What would happen to the aluminium ring if the primary coil current was increased? Then a student suggested that the ring is placed in liquid nitrogen before being slotted over the iron core. Suggest what effect this would have when the AC power supply is switched on. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, you can see that if the primary coil current was increased, well then the induced current in the ring will be greater, because you'll see that there'll be a greater flux linkage from the primary coil, so therefore there'll be a greater change in flux linkage in the secondary coil because it's alternating plus or minus plus or minus. So therefore the magnetic force on the ring would therefore be greater, so be pushed higher, so therefore the ring will be pushed to a greater height before it reaches an equilibrium with the forces acting down, so therefore it starts to, quote, float. Okay. Now what would happen if you put the liquid nitrogen in? Well, if you put the liquid nitrogen in, well then the resistance in the ring itself will be reduced because it's a lot lower, colder temperature, so therefore a much larger induced current will flow in the ring, so therefore the magnetic force pushing the ring upwards will be even greater, so therefore it might even go up and hit the ceiling because you've got such an upwards magnetic force, because the resistance will be so low in that particular aluminium ring. The next question says, a power station is connected to towns by a cable of total resistance 10 ohms delivering 50 megawatts. Calculate the power losses in the cable if the power supplied to the town is directly from the generator of 25 kilovolts or after being stepped up to 400 kilovolts. Then a power cable of total resistance 20 ohms is used to deliver 2.0 megawatts at 33 kilovolts to a heavy industrial plant. Determine the power wasted in the cable. Then, a portable diesel power generator is capable of producing 4 kilowatts of electrical power at a voltage of 240 volts for use on a remote farm that is not connected to the national grid. If cables of total resistance 1.2 ohms deliver the electricity to the farmhouse, determine the power loss as heat in the cables when the generator is running at 4 kilowatts, and then the minimum size of the voltage available in the farmhouse. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using the equation I equals P over V. So we can work out what I is going to be, because it's going to be 50 times 10 to the 6 megawatts into watts, divided by 25 times 10 to the 3 kilovolts into volts. So we get 2000 amps. We then say P equals I squared R. That's the equation to work out the power dissipated in electrical cables. You're given that on your equation sheet. So it's 2000 squared times by 10 is 40 megawatts. You can do the same equation when it's been stepped up to 400 kilovolts, and you get 0.16 megawatts, which actually proves you mathematically why we step up the voltage in the step-up transformer. Again, we can use the same equation again here in question 2. We say I equals P over V, work out I to be 60.6 amps. We therefore say power lost is equal to I squared R, pop in all those values, and we get 7.3 times 10 to the 4 watts. Next question, again we're using that same principle. I equals P over V, 4000 divided by 240, remember 4 kilowatts turns into watts, so it's 16.7 amps. We then say P equals I squared R, pop in all the values, and we get 335 watts. So what's the minimum voltage available? Well, At this point, the voltage drop across the cables at full power is 20 volts because we know V equals IR. We know I from the question is going to be equal to the previous question is 16.7 amps. Times it by the value you can work it through for R, which you know is 1.2 ohms from the information given in the question. So therefore, the voltage available at the farmhouse must be 220 volts because it starts at 240. We lose 20 volts of lost volts in the wire, so therefore we're left with 220 volts left behind. The next question says, state two situations in which a charged particle will experience no magnetic force when placed in the magnetic field. Then a charged particle moves in a circular path when travelling perpendicular to a uniform magnetic field. By considering the forces acting on the charged particle, show that the radius of the path is proportional to the momentum of the particle. Then a cyclotron is a circular particle accelerator. In a particular cyclotron, the flux density of the uniform magnetic field is 0.48 Teslas. Calculate the speed of a proton when the radius of its path inside the D is 190 millimeters. Then calculate the time taken for this proton to travel at a constant speed in a semicircular path of radius 190 millimeters inside the cyclotron. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to just learn when a charged particle experiences no magnetic force inside a magnetic field. A, when it's moving parallel to the magnetic field, and B, when it's not moving relative to the magnetic field. The next one, we've done this before. We've said that the centripetal force equals the magnetic force, so BQV equals mv squared over r. We can rearrange it. We can make r the subject. R equals mv over bq. B and q are constant, so r is proportional to mv. We can then rearrange this equation and say V equals BQR over M. Pop in all the numbers. Now remember, 90 millimeters turns into meters. We pop that through. Remember, we know the mass of a proton is given to you on the equation sheet, 1.67 times 10 to the minus 27. We know the charge of a proton is 1.60 times 10 to the minus 19, given to you on the equation sheet. So the values give you 8.7 times 10 to the 6 meters per second. Now just be very careful in this next question because it's asking for the length of a semicircle. So the length of a semicircle, okay, not the area, but the length is half of the circumference. So it's pi r. So therefore the time taken is the length which you travel, which is the circumference of a semicircle, which is pi r, over the velocity. Pop in all the values, we get 6.8 times 10 to the minus 8 seconds. The next question says, a circular coil of diameter 140 millimeters has 850 turns. It is placed that its plane is perpendicular to a horizontal magnetic field of uniform flux density 45 milliteslas, as shown in figure 1. Calculate the magnetic flux passing through the coil when it's in this position. Then the coil is rotated through 90 degrees about the vertical axis in a time of 120 milliseconds. Calculate the change in magnetic flux linkage produced by this rotation, and then the average EMF induced in the coil when it's rotated. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say that phi equals magnetic flux is BA. So you work it through, remember it's a circle, so you're going to do pi r squared, where r is half the diameter, given the diameter in millimeters, converted to meters, and half it to get the radius. Pop those all through, so we get 6.9 times 10 to the minus 4 Webers. Then this next one, the change in magnetic flux linkage. Well, we know that if it's rotated 90 degrees, it'll go to 0, but what does it start at? Well, we know that it starts at MBA, so therefore we know it's the value we just worked out, which was going to be BA, multiplied by N, which was 850, so it's 0.59 minus 0 is still 0.59 Weber turns. Now the average induced EMF is this value divided by the time, so therefore you divide this value by 0.12, so it's 4.9 volts. The next question says, a simple loudspeaker consists of a cone, a coil of wire and a magnet. The cone and the coil are attached to each other and are free to move. An alternating current in the coil causes the cone to oscillate. The loudspeaker is mounted in a wooden box. A cross-section through the loudspeaker is shown. The student made the following observations. When an alternating PD is applied to the cone oscillates. The frequency of the oscillation is the same as the frequency of the PD, and at particular frequencies the box vibrates with a large amplitude. Explain these observations. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, you should be aware that you know that an alternating potential difference will cause an alternating current in the coil. Now, because it's a current carrying conductor and it's inside a magnetic field, those two fields will interact and therefore it will experience a force. So the current is alternating, so the force will change direction as the current changes direction. So therefore, this will cause the cone or the box to go into an oscillation, so therefore the frequency of the oscillation will then equal the natural frequency of the oscillation of air in the box. Now therefore that gives you a maximum energy transferred and the amplitude of the vibration increases. That's resonance. Now what this question is doing to you is actually recalling you understand from periodic motion. It can do that because in paper 2 they can ask on any concept from paper 1. The next question says, the diagram shows below an AC waveform that is displayed on an oscilloscope screen. The time base of the oscilloscope is set at 1.5 milliseconds per division and the Y gain at 1.5 volts per division. Firstly, calculate the frequency. Secondly, calculate the peak voltage. Third, calculate the RMS voltage, and then state and explain the effect on the oscilloscope trace if the time base is switched off. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, the trick is you're going to have to use all of the wave because that will lower your percentage uncertainty. So to work out the frequency, well, you know the time period for 1.5 waves because that's the entire thing on the screen. So for 1.5 waves, you're going to get 15 milliseconds because it's 10 squares, each with a division of 1.5 milliseconds. So therefore, you can work out what the frequency is going to be because the time period therefore for one cycle is going to be 10 milliseconds. So therefore, it's 1 over 10 milliseconds in seconds. So therefore, it is 100 hertz. Now again, you can look on the screen and work out the peak voltage to be 2 times by 1.5 volts because that's how much each square is worth, so it's 3 volts. The RMS is going to be the peak divided by square root 2, so it's 2.12 volts. Now, if you turned off the time base, a very common question, you would no longer get a wave pattern. Rather, you would get a vertical line, which would be twice the length of the peak voltage because it's peak to peak, so it's positive and negative. Okay, and then the trace will no longer move horizontally, so therefore it would just be creating that vertical line. The next question says, a technician is designing a transformer. Calculate the number of turns needed in the transformer and then state 2 methods of reducing power losses from a transformer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using the transformer equation. Vp over Vs equals Np over Ns. Remember, V is directly proportional to N. Pop it all through, we get 300 turns. That feels right because the potential difference has gone down from 240 to 90, so therefore the number of turns will go down as well from 800. Now, you've got to know all the ways we make a transformer efficient. So that could be use a wire with a greater diameter because that will reduce resistance. Use a wire with a low resistance. Use laminations in the core to prevent eddy currents. Use an insulated laminate, the same thing. Okay, use materials with a low hysteresis in the coil to stop energy loss when you've got an alternating magnetic field. Okay, and you can also reduce the heat in the circuit by cooling it down. The next question says, the national grid is a network of cables and transformers connecting power stations to consumers. A 1,500 megawatt power station has a series of transformers that step up the output PD from 25 kilovolts to 400 kilovolts. Calculate the ratio of turns from the first primary to the last secondary coil in the power station. Assume the transformers are ideal, that means it doesn't lose any energy to the surroundings. The resistance in the transformer cables is 30 ohms. Determine the power loss in the transmission cables. Then calculate the efficiency of the transmission system. Then the student asks why the electricity is stepped up for electrical transmission since power loss is equal to V squared over R. Explain why high PD is used for electrical transmission and correct the misconception. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, once again, we're using the transformer equation. So NS over NP equals Vs over Vp, so therefore we can work it through to be 400,000 over 25,000. Remember, it's kilovolts and kilovolts, so we turn those into volts, so we get our ratio of 16 to 1. Now, what's the power loss? Well, we know current is equal to power divided by potential difference. We've got our power, okay, to be 1500 times by 10 to the 6. We divide it by the potential difference of 400 kilovolts, because that's what it's going to be in the transmission cables, because it's gone to 400 kilovolts. So it's 3750 amps. We know the equation for power loss in a cable is I squared R. Pop in all the values, we get 4.2 times 10 to the 8 watts. The efficiency, therefore, is the useful output over the total input. We know that the useful output is going to be the 1000, so the useful output is 1500 times 10 to the 6 minus the power loss in the cable. We then divide it by the 1500 times 10 to the 6, because that's our total input, so it's 0.72%. Now, why is this a misconception? Well, if you step up the potential difference, the current decreases by a factor of 16, so because it's, you know, it links through in that particular logic. So therefore the power loss in the cable is due to the heating effect of the current, so we don't tend to use P equals V squared over R. It's more due to the current and this heating effect, so we can use P equals I squared R. So therefore you could possibly use P equals V squared over R, but that's not the potential difference. That's not the potential difference of one instance. It's from the start to the end, so it's not 400,000. Okay, so therefore it's easy to use the current through the cable, because that's constant through the cable, because it's one long series circuit. So because V isn't a constant factor in the cable, we can't use that in the equation, but we can use current. So we use P equals I squared R. The next question says, calculate the length of the copper wire that has a diameter of 1.6 times 10 to the minus 3 meters and a resistance of 25 ohms. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Then the resistance of copper wire is not zero. Explain why this fact leads to the use of the alternating current rather than the direct current when transmitting electrical energy. So pause the video now, then unpause the video when you want to go through your answers. Right, so this one is revision from paper 1 again. So we know that resistance equals resistivity times by length over area. Now again, that equation is given to you on your sheet. So L equals RA over rho. Pop in all the values. Now remember, area is pi r squared. So we take our diameter and we half it before we square it. So we work it through, the area to be 2 times 10 to the minus 6 meters squared. Pop in all the values and the length is 3000 meters. Now again, the resistance, okay, will lead to energy loss, power loss, energy dissipated of the surroundings. So therefore we know that because the power loss is I squared R, so the bigger the value of R, the bigger the loss of power loss. So therefore you can also say that you want to use alternating current, because that will lower the current, which will lower the loss of heat or energy or power and reduces that voltage drop. And that happens because alternating current can be used, it can be transformed in a transformer, but direct cannot, because it needs a change in magnetic flux linkage, which doesn't occur if you're using a direct current. So thank you very much for listening to this revision session. If you've been successful and learnt in today's revision session, you should be able to answer A-level physics examination style questions on magnetic fields, assess your understanding on magnetic fields for A-level physics, and understand what topics you need to improve upon for A-level physics in magnetic fields. So thank you very much for participating in this revision session for magnetic fields, and have a lovely day.